Hello, hello, hello. Mic test one, two. Hello, hello, hello. So if una join the class, uh, class don start o. Una join class. If you join the class, just wave. Once I see 5 hands, I'll start the class. So just wave. If you enter the class, you wave. Okay. I don't see like one, two. Just two hands. One, two, three. Okay. So I never see reach 5 hands, so Mona do. Time no dey o. I go off audio. I still dey, but make I off audio. Okay, I think I will have to start class. Every other person joining can join us later. You get. Where is my? Okay. Yeah, we'll have to start. Okay. So, good evening, everybody. My name is Godson, and I will be taking you on this chemistry class on organic chemistry. Um, First of all, as I mentioned earlier, if you have issues or questions while I am teaching, just type in the live chat. I will see what you typed and then respond to it accordingly. I hope this is clear. Now, please, if you can hear me, just type I can hear you so that I would confirm that my audio is clear. You get, just confirm with me if you can hear me, just type I can hear you so that I will be sure that my audio is clear. Okay, if that is done, quickly, just one person and I'll continue class. Time no deal. One person, just one person say I can hear you, so I'll know. Because my monitor guy is no day with me here. Okay, very good. So let's move ahead. So as I said, my name is Godson and I teach chemistry. I'm going to be taking you on this particular part of the study. Please, if you come in here, just click like for that video. Just like my video. Like the video. Maybe we just do small, small. Um, Having said that, today we are going to start with the introductory parts of this study. And in the introductory part of this study, we'll be considering these particular headings: Introduction to Organic Chemistry, the classes of carbon atoms in a chain, special properties of carbon, which includes catenation, electronic configuration, bonding in organic compound, and hybridization. Then we are going to finally talk about isomerism. Now, this is a very broad study, but your understanding of this particular aspect will make it easier for us as we go further. The next part of the study we will get into is elemental analysis of organic compounds. That's where we'll now talk about chromatography, separation techniques, empirical formula, before we now get into the organic compounds gone gone. So, as I said, in this study we are going to concentrate on these things. So let's get right into it. Anytime you think about organic chemistry, the very first thing that should come to your mind is carbon. That's the first thing. So anytime you think organic, the first thing that should come to your mind is carbon. So organic chemistry is simply the chemistry or the branch of science that deals with the study of carbon related compounds. Carbon related compounds. Carbon related compounds. Once you are looking at a carbon related compound, you are considering organic chemistry. But there's an exception. The exception to carbon related compounds that are not organic are um, oxides of carbon. When I say oxides of carbon, I mean CO2 and CO. If you want to consider an organic compound, carbon 2 oxide is a compound of carbon. Carbon 4 oxide is also a compound of carbon, but they are not organic. I take it again. Organic chemistry is the branch of science that deals with the study of carbon related compounds, except these things. Number one is oxides of carbons, and I've mentioned them. The second one is the trioxocarbonate 4 acid. Trioxocarbonate 4 acid. Trioxocarbonate 4 acid is H2CO3. And then finally, you have your carbonate salts. So anytime you are considering organic chemistry, these three are not involved as organic compounds. So if I happen to write something like C2H6, CO2, and C triple bond to NH, and I have these three compounds, and I ask you, which one of these is not an organic compound? This is A, this is B, this is C. So please answer this question. Which one of these is not an organic compound? Yes. Which one of these is not an organic compound? So let's put our answers out there. Okay, so yes. Let's put our answer out there. Which one of these is not an organic compound? Oh yeah, Mona indicate to. Mona indicate. Which one of these? Okay, very good. So Godson says it's B, and that's what it's supposed to be. It's B. Very good. Now let's continue. Having said this, as I said, once you are considering organic chemistry, you are looking at any compound of carbon, but you have to exempt oxides of carbon, triazocarbonate, 4 acid, and any carbonate salts. Remember, carbonate salts are salts that contain carbonate ion. The carbonate ion is CO3. So once you have a salt, for instance, okay, let me take this out. So if you have something like this now, Na2CO3, this is a carbonate salt. If I have NHCO3, this is a bicarbonate salt. So these things are not organic even though they contain carbon. However, every other thing that has to do with carbon, every other compound that has to do with carbon is relatively classified as an organic compound. Now, why is it that we have to study organic chemistry as a special part in chemistry? Because carbon is special. And because of that specialty, you find out that there are so many compounds that are formed with respect to carbon. Before we get to that part, I would like us to understand the different classes of organic compounds that can exist. We are still going to discuss these things in details, but one of the reasons I like introducing this concept is so that when I'm referring to certain things as we go down in our descriptions, it will not be new to us. So, the general classification of organic compounds. We'll start with the first classification. They are first classified into two broad parts. The two broad parts of organic compounds are your hydrocarbons and your non-hydrocarbons. I presume you guys did this in your biochemistry part of Bio 151. So it's not going to be an issue. So when you say something is a hydrocarbon, it simply means that it only contains hydrogen and carbon. Non-hydrocarbon implies that it contains something else that is not hydrogen and carbon. These things are simple things, but it's important I mention them. For instance, let's take for instance, you have this compound. If I have C2H5OH and I have C2H2 and I have C2H6, and I ask, amongst these compounds, which one of them is a non-hydrocarbon? Yes, from what I just explained, can we please choose the one that is a non-hydrocarbon quickly? Okay, the font is too small. Okay, I'll have to do that. Thank you very much. I would do that now. Let me correct the font. Address what you just said. Okay, I would address that. The font. Someone said that the font is too small. I will do that later. But try answering this question so that we'll move ahead. Which one of these three is a non-hydrocarbon? Obviously, it is A. So why it is simply not, why we will classify it as a non-hydrocarbon is very simple. And what is the simple reason? It contains something that is not carbon and hydrogen. Once it contains only carbon and hydrogen, hydrocarbon. If it contains any other thing, non-hydrocarbon. Let's move ahead. Now, as I was saying, I'll try to increase the text. Sorry about that. Okay, so as I was saying, you have a classification into hydrocarbon and non-hydrocarbon, and after that classification, you go further. Now, moving ahead, hydrocarbons are now classified into two broad parts. You have what we call the aliphatics, and then you have your aromatics. Under hydrocarbons, you classify hydrocarbons into two: aliphatics and aromatics. Now, I'm going to use, I feel that we all should know some basic things in organic chemistry, which means when I mention single bond between carbon, you should know that is one bond, one line. You get, this is the line structure. Okay, this is actually the normal structure. We'll discuss structures in organic chemistry anyway. If I have this between these two carbon, you have a double bond. If I now have this, you have what we call a triple bond. Now, just have that in mind. Single bond is just one line, indicated by one line. Double bond is indicated by two lines between the carbon atoms, and triple bond is indicated by three lines. So when I say single bond, double bond, or triple bond, that's actually what I mean. I believe you have some basic understanding of organic chemistry. Now, with that said, if you consider your aliphatics, aliphatics are hydrocarbons that possess localized multiple bonds if present. What do I mean by that? If, for instance, you consider this particular compound now, how will I know if this compound is an aliphatic? It is an aliphatic if and only if this double bond that is here does not change its position regularly. If it was an aromatic, one of the most important aromatics you would have is benzene. And in the aromatic structure, you will have constant movement of this double bond. That is actually what gives it its aromatic property. When you are considering aromatics, the major feature or what makes a substance aromatic is because it possesses movable double bond. Let's consider this structure. Now, in the case of benzene, this is the first structure, and after a while, you will notice that this particular double bond that is here will move to this next one, and it will be here. This one will move to the next one, it will be here. This one will move to the next one, it will be here. So notice something. There is a regular movement of this double bond around this particular cycle, and because of that, this is considered an aromatic. So aromatics are characterized by movable or delocalized double bonds, while in the case of aliphatics, if the multiple bonds are present, the multiple bonds are localized, they do not move. That's exactly why when you consider Kekule's structure of benzene, his resonance structure is like this, which indicates that this double bond is constantly moving around. So have that in mind, that if you want to differentiate between aliphatics and aromatics, the both of them are classified under hydrocarbons. However, aliphatics are characterized by non-movable multiple bonds, while aromatics are characterized by delocalized or movable double bond around a benzene ring. I presume this is clear. If you have any question with respect to what I just explained, please ask your questions now. Okay, now I also noticed something. It seems some of you are not where you guys are not like exactly where we are. Once you join the class, you would see, if you click on your screen, you will see a live, like live is written on the screen, the display screen. So all you need to do is click on that particular dot there so that it will take you to where we are currently. I don't know if this is heard. Okay, so basically, yes, what's our answer? What do we think? I hope this is clear. Is there any question or confusion? If there's no confusion, just type no confusion so that I can move ahead. I'm trying to carry everybody along in this class. I just want one person to indicate if there's any confusion or not so I can continue. Just one person. I'm still waiting. If there's a confusion, you need some things cleared, ask the question now. If not, I want to move ahead. Okay, I'll just have to move ahead. Now, as I said, that the differentiating factor between aliphatics and aromatics is, in the case of aromatics, when this double bond is present, it moves from one place to the other. That's aromatics. That's why in aromatics we say it is the hydrocarbon that possesses delocalized double bond. That is to say, double bond that moves around. That is the aromatics. But aliphatics possess localized multiple bonds if they are present. That is to say, when you say something is localized, it means that it stays at one place. So that is the difference between the two of them majorly. Now, having said this, at this point, I would go further in the classification. I'm taking my time to actually outline these things, simply because if you don't understand these things and we go further, we will have issues. I would not want to come back to describe these things again. Okay, so moving ahead. Aliphatics, here aromatics, the major group is benzene. Any compound that has a benzene related structure is under aromatics. Once you have a benzene structure, you classify it as an aromatic. We will get to discuss these things in details, your benzoic acid, your phenols, your toluenes, and the rest of them. Good. Okay, so the aliphatics. Now, aliphatics are now classified into acyclic and cyclic. Acyclic and cyclic. When I say acyclic and cyclic, acyclic means not cycle. Cyclic means cycle. You get? So which means if I have a chain of hydrocarbon that is straight chained, something like this, it's not joined in a circle, automatically this one becomes an acyclic hydrocarbon. But when I have a chain that forms a circle, this one is now what we refer to as a cyclic hydrocarbon. So just have that in mind. This is cyclic, this is acyclic. You get? So just always have that in mind, that cyclic means open-ended chains, long chains, straight chains, while cyclic are the ones that form the circle or are in cyclic form. Okay, I'll have to take this out and continue. Now, having mentioned this, the acyclic is now further broken down. I'm taking my time to discuss this, for I know my reasons, because once I start moving ahead, I would not want to be referring to these things anymore. These are very basic things that you should have done in your secondary school, but I'll still try to explain it well. Now, under the acyclic, there are three major we have. We have alkane, we have alkene, and then we have alkyne. Then when you come to the cyclic, all you need to do is just put cyclo and then put alkane. The next one will be cyclo alkene, and the next one will be cyclo alkyne. Now let me just say one or two things about this before I continue. I presume you are still seeing this. Let me just confirm that my screen is still rightly positioned. Okay, yeah, it is. Okay, so the point about this thing is we should know these things. Alkane, once you hear alkane, it's hydrocarbon that has only single bond. Once you notice that it's only single bond that is there, you see carbon carbon and it's only carbon and hydrogen, and there is no double bond, there is no triple bond, it's only single bond you are seeing. It's alkane. Now when it is now in a circular form, like when I now have this thing now, you notice that everything here is single bond. Because it is now in a cyclic form or circular form, this will now become a cycloalkane. Very basic principle. Alkene will now be one that has at least one double bond. So if I now put something like this now, and then I put this now, because there is double bond between carbon atoms, this is an alkene. Please note, alkenes possess double bonds, not between carbon and any other atom, it's between carbon and carbon. So this case now, this is an alkene. You know why I'm saying this is, some of you might see this compound now, and somebody's village people will tell them, see double bond, so this is alkene. First of all, alkene is a hydrocarbon. The only thing that is found there is carbon and hydrogen. The only thing that will be found in alkene is carbon and hydrogen. That's number one. So automatically, it's not because there is just double bond though. Check where the double bond is. Once there is a double bond between two carbon atoms, that is when you refer to it as an alkene if it is a hydrocarbon. So that's that basically. So as I said, alkenes, double bond, alkynes, triple bond. We've not come into discussing these things in details. I just want to highlight them so that when we are mentioning some things as we go further, it will be easy to take note of. Okay, now having said this, I will now highlight some of the non-hydrocarbons that are very important. The very important ones that we need to know are your alkanols. They are very important in the body system. You have your alkanoic acids. The next one is your alkanals or aldehydes. That's where your sugar guys comes into play. Aldehydes. Your alkanones or ketones. You have your ethers, your esters, the fruity smell, and so on and so forth. A amine group, very important, and amide group. So we are going to be considering these things in details, but that is as the study goes down. I'm just trying to give you a broad understanding of the things that we are going to be understanding, a general or a tabular description of the things you are going to be seeing so far in this study. So that is that. So you can screenshot if you want to keep this, or write if you are writing. Anyhow, the point is just take note of it. Okay. Now, having said that, we will have to move ahead to other things for want of time. Sorry, let me just resolve one internet issue here. I'll get back to you guys. Um, where is the issue? Just to make sure that the class is going smoothly. I'm cross-checking to see if there's any glitch anywhere. Okay, that has been resolved. Okay, so I think we can move on at this point. Yes, we can. Okay, now that's that generally about the classification of organic compounds. This is what we refer to as the classification, the general broad classification of organic compounds. These are the important ones you need. As you go further, you will see things like diazoniums, the imines, and so on and so forth. Those ones are like derivatives of these ones here. So have that in mind. Okay, we are done with this on the screen. We need to move ahead to the next talking point. Now, the next thing I'm going to talk about as part of the introduction is what I refer to as classes of carbon atoms. But before I continue, please, I hope we are following. Okay. Okay, someone said I should re-explain aliphatics. Aneke Victor. Okay, I will come back to that. I'll come back to re-explaining that. Okay, let me just re-explain. Now, please, as I said before, aliphatics simply means that if there is a double or a triple bond there, that double or triple bond does not move. It stays one place. If you look at the benzene ring, if you have, okay, let me just put up the structure so that you will get what I'm saying. Once you consider the hexagonal structure of a benzene ring, what is put in the center is circle. This circle here indicates that whatever multiple bond here is moving round and round and round. We are still going to discuss those multiple bonds, but just have this in mind that the indication of this circle is a resonance structure. This is a resonance structure which indicates that that particular bond that we drew as this is not one place. It's constantly changing position. That is one major thing about aromatics. But if it is an aliphatic, if it contains a double bond at all, that double bond or triple bond will stay one place. E no go dey move. That is the difference between aliphatics and aromatics. Somehow the name is not related to the definition in most cases, or in this case now, but it's something that I believe can be easily understood. So Chukwebuka Victor, I presume I have answered your question. Now please, if you are not following, make una dey indicate. You get. So let's move ahead. Now, the next part I want to talk about is classes of carbon, not organic compounds. Classes of carbon in a chain. Why I want to discuss this thing is because as we go further in the study, especially when we enter things like alcohol, it will be easy to understand classification of alcohol and the types of reactions in alcohol if you understand the classes of carbon. You get. And what are the classes of carbon? Okay, so classes of carbon in a chain. So once you have a chain of organic compounds, let me put out a chain 1, 2, 3, 4, 5, 6. I'll do this quickly. I'm moving to the main things. So once you have a chain of organic compounds, let me number them 1, 2, 3, 4, 5, 6, 7, 8. Now, each of these carbon atoms in this chain represents a class. And what are the 4 classes? Primary. Some of you are in my last class, so you should know this. Secondary. Tertiary. And quaternary. Wrong spelling. Quaternary. Okay, so you have that. When you are considering classes of carbon, the first thing you need to check is the positioning of the carbon atom. That's number 1. Then the second thing you will use to understand the classes is how many carbon atoms are directly attached. So let's start with the first one. A primary carbon atom is number 1, a terminal carbon atom. That is to say, it is a carbon atom that is at the last part of the chain. I take it again. The first feature of a primary carbon atom is it is terminal. When you say something is terminal, it means that it is at the end, the last part of the chain. After that carbon, there is no other carbon atom. If you consider this structure now, can you please outline? I will give you one of them. I'll give you one, you tell me the rest that are primary. Carbon number 1 is the last in this end, so it is primary. I take it again, primary is the one at the end. So can you please list the other carbon atoms that are also referred to as primary in this chain? Yes? Put out your reactions quickly. Put out your reactions quickly. Put out your reactions. Yes, I'm still waiting. Which ones are primary? I don't call one. The one will be primary based on my explanation is carbon number 1. Can you give me the rest of the carbon atoms that are also primary carbon atoms? Oh yeah, I'll do. We have a lot to discuss so that we'll finish our talking points for today. Oh yeah, oh, just 1 or 2 answers and then I move ahead. Quickly, there is no time. These are like intermediary things that we need to know. You get, so that when we are explaining the complex parts, it's just easy and we don't need to stress too much. Yes, 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 yes. Anybody? Nobody won't give answer. Wetin dey sup? Abi una no understand? Okay, Onyeka Anyako said 17865. 1786. Correct. Yeah, yeah. Nice. Yes, nice, nice, nice. You guys are getting it. They are all correct. Okay, make I continue. Somebody say 4. How is 4 primary? Eh? Mesomer wisdom. I don't think 4. Let's take the definition now. Let's take the definition. We said it is the last carbon. Which ones are the last? This one here is on the last. This one, after this one, are you seeing any other carbon? No. So this is the last terminal. After this carbon, you are not seeing any other thing here. So this carbon is terminal. But if you say number 4, after number 4, you have number 5 now. So this cannot be terminal. So whenever you think about primary carbon atom, if you are writing or if you have a jotter, I would also advise you please get a jotter and a pen so that you take note of these important factors. So a primary carbon atom is a terminal carbon atom that is directly attached to only one carbon atom in the chain. I take it again. A primary carbon atom is a terminal carbon atom that is directly attached to only one carbon atom in the chain. So the first thing we used to know primary here is that it is terminal. Second thing is that, which is actually the most important one, is that anything that is primary is directly attached to only one carbon atom. It is very important you take note of this. So if you have this carbon here, please, I did not say only one atom. Specifically, mark my words, I said only one carbon atom. Reason I'm saying this, if we consider, okay, I will put out a structure. If you look at this structure now, this one I just drew now, you will notice that this particular carbon number 1 is attached to 4 atoms, 1, 2, 3, and 4. But the only carbon atom it is attached to is just 1. When you are considering classes of carbon, you are not considering the number of atoms that are attached to the carbon. You are only considering the number of carbon atoms attached to it. So I take it again. A primary carbon atom is a carbon atom that is directly attached to only one. It's a terminal carbon atom that is directly attached to only one carbon atom in the chain. And you find out that number 1, number 7, number 6, number 8, and number 5 coincide with that. Check it now. This carbon, only this carbon in whole. This one here is directly attached to number 2, only number 2. Carbon number 5 is directly attached only to number 4. But if you take something like carbon number 3 now, you see that carbon number 3 is attached to carbon number 4, carbon number 3 is attached to carbon number 2, and carbon number 3 is still attached to carbon number 8. So it's not primary because it's not only attached to one. So you have this attached to one carbon. Now we get common sense. So secondary go be waiting 2 carbon. Normal. Secondary carbon atom is now the carbon atom that is attached to only 2 carbon atoms in the chain. Oh yeah, with our common sense, I believe we are smart people. We are in 100 level, for goodness sake. We said secondary carbon is the carbon atom that is attached to 2 carbon atoms. Which one is secondary here? I don't need to give you guys the answer. You just tell me quickly. Which one of these is secondary? Which one of them is secondary? Yes, yes, yes. I'm waiting for your answer. Which one is secondary? Sharp, sharp. Sharp, sharp. Oh. We don't, no be this one we can't do today, sha. I'm gonna do. Exactly. Omenazu praise, you are absolutely correct. It's carbon number 4. If you check it, let's go back to the board. Mona post na answer, make I know say person dey my class. Okay, so if you check this structure, you will see that this carbon now is attached to number 5, 1, is attached to number 3, 2, and it is only 2 that is this carbon is attached to. Some of you might have said 3 or thought about 3 and 2, but if you notice, carbon number 3 is attached to number 2, number 8, and number 4, which is carbon that is attached to 3 is not secondary. Secondary is attached to only 2 carbon. Tertiary will now be attached to only 3 carbon atoms, and therefore quaternary finally will be attached to 4 carbon atoms. So you have that. Oh yeah, so you guys should list. Which one is tertiary? Here, just write your answers. Tertiary, which carbon? Quaternary, which carbon? So move ahead. Oh yeah. Okay, okay. Dynasty eBay, I presume you've gotten my correction. Oscar Samuel, I also presume you've gotten my correction to this. You don't need to retract your answers though, but just have that in mind. I hope it's clear. Dynasty and Oscar, can you please respond if you've understood? If you don't understand, I can re-explain. Una talk oh yeah, oh, time no day. Okay, yes, carbon number 3 is tertiary. Very good. Which means that carbon number 2 is quaternary. Very simple. Please, if you would want me to re-explain, okay, just indicate. I did live with you people. I did see una talk. If you want me to re-explain, you could just ask me to do that, and I'll do that. Okay, I think we are done with the classes of carbon. As I said, another thing I would like to say before I continue. You know, if you notice, this is a YouTube channel, which means it go good if you subscribe. So subscribe, and then secondly is like this video. If you enter my class, you like the video, very good. 2 is for quaternary. That's this gods in Chukwemeka and my sister Asha, Nancy. Well done. Let's continue now. Having said this, we are going to continue into the next part of the study. This part now is another very heavy part. Another very heavy part, which is also still amongst the basics. And that part is what we refer to as, okay, before I get into that. Now, if you notice, there are over 2 million organic compounds that are existing. When I mean over 2 million. Check it. You have about 118 elements. And carbon, being one of the 118 elements, produces or has produced over 2 million. It's not like it's just 2 million, over 2 million. The number of compounds that exist in this world that are organic compounds is more than 2 million plus. You get? So the implication is that there has to be something special about carbon that enables it to be able to form as many compounds as it wants. You get? And because of that, that is one of the reasons organic chemistry was created. They notice that this carbon is just doing too well. The number of compounds that are carbon based are too much, and because of that they had to take out a special part of chemistry to study it. Now, what are those features that make carbon so special? That is what we're going to be considering. So the next subheading we're going to be considering are special properties of carbon. Special properties of carbon. Okay, now before some of you start asking questions, but these are not things that I find I saw a particular scheme for UNN students, and that study, all these things are under nature of organic chemistry. You get? So organic compounds, I meant to say, all these things we are discussing are things under it. You get? I'm taking my time to discuss it this way so it will be easier to understand and simplified. You get? We'll still touch all those things. I'm following your curriculum as well as every possible university curriculum and areas we should all touch. But these are the introductory parts. I said that in our next class, we're now going to talk about elemental analysis. Elemental analysis is where this thing comes into play, where we talk about your your chromatography, separation techniques, empirical formula, what are the different tests. We'll discuss those ones under elemental analysis, and that's in our next class. But these things are the basic things you need to know before you call yourself an organic chemistry student. Now let's continue. Now, what are those special properties that enables carbon or gives carbon an edge over every other compound that makes it to be able to form as many compounds as possible? We are going to be considering four major characters or four major properties, starting with the first one. The first one is what we call catenation. Catenation is simply the ability of an atom to form chains with other atoms of the same element. I take it again. Catenation is the ability of an atom to form chains with other atoms of the same element. So once you have an atom and that atom can join with another atom of the same element, another carbon, another carbon, another carbon, another, just they join, they go. What is happening here? The ability to form this chain is what we refer to as catenation. You get? So once you have a particular organic compound or any element at all that has the ability to join with itself to form long chains, that is what we refer to as catenation. Now, amongst every element that exists, carbon is the only element that has shown the most effective form of catenation. That is why it is able to form many compounds. So you will notice something. When two carbon atoms join, compound don form. 3 join, compound form. 4 join, compound don form. So you will notice that even up to 1 million. Take for instance your proteins, which are polymers of your amino acids you get. Now when the amino acid join to form your dipeptides, it increases to the polypeptides and so on and so forth. An amino acid usually, sorry, a protein chain, in most cases, some texts or some studies will tell you that you have to have at least 500 units of amino acid and so on and so forth. So you will notice that catenation gives it that edge, such that carbon can join to carbon to carbon to carbon, and you can have a variable number of compounds just by joining or attaching carbon atoms. So that's that basically. So that is that for catenation. I take it again. Catenation is simply the ability of an element or an atom, sorry, the ability of an atom to join or to form long chains with other atoms of the same elements. Basically, that is catenation. So you have that in mind. Okay, do I need to write that down? Okay, let me just write that down. Ability of an atom to form long chains with other atoms of the same elements. Of the same elements. So that's catenation for you. So whenever you consider catenation, that's what it means: the ability to join, and form long chain, provided at the same element. And the element that has the most effective form of catenation is carbon atom. Okay, moving ahead. The next property we are going to consider is the electronic configuration of carbon. That is another special thing. Now, before I get into this, let me just take this out and describe one or two things about electronic configuration. You guys should have probably done this in your first semester or during your secondary school days, but let me highlight a few things that are very important if you must understand this. The very first thing I'm going to highlight is that, number one, electronic configuration is the arrangement of electrons in the orbital of a particular atom. Once you are arranging electrons in the orbital, what you are simply doing is that you are writing the electronic configuration. Now, every time you are writing electronic configuration, it is actually dependent or based on what we refer to as quantum numbers. The 4 quantum numbers that are considered are the principal quantum number, the azimuthal or subsidiary quantum number, You have the magnetic quantum number. Magnetic quantum number. And finally, you have your spin quantum number. Now, I'm just going to highlight, I'm not discussing these things in details. I'll just highlight what these things imply. The principal quantum number simply tells us about energy levels. Azimuthal quantum number talks about subshells and shapes. Okay, back to this. When you are considering the energy levels, you are looking at energy level 1, 2, 3, which is usually represented by the letters K, L, M, N, and so on and so forth. You guys probably did this in last semester, where you talked about your Paschen series, your Lyman series, and so on and so forth. So those things are indications of the energy levels. In subshells, the subshells we are going to be discussing are the SP, D, and F. However, with respect to this organic chemistry wey we dey do, na only S and P we go discuss. You get. You could actually look up studies on energy quantization of atoms later. Magnetic quantum number, what it does is it tells us number of degenerate orbitals. Degenerate orbitals. Now, see what I mean by degenerate orbitals. You know, if you come to S now, you only have one block. You go to P, the degenerate orbitals are 3, 1, 2, 3 in P. If you come to D, the number of degenerate orbitals in D are 5, 1, 2. So you have 1, 2, 3, 4, 5. So the small blocks is what indicates the number of small blocks is the magnetic quantum number. In S, you have only one small block. In P, you have 3 small blocks. In D, you have 5. Then finally, you have your spin quantum number, which tells us the rotation of electrons. And you can only have 2. That's one will face up, one will face down. That is all, basically. So that is that about the quantum numbers. Now, how do they apply or relate to the electronic configuration? But before I go into that, please, I would like to confirm, are you people still following? Abi all of una don go sleep? Yes, una still dey follow? If you are following, just type I am following. Oya o, muna type. If you are following, type I am following. If you are following, type I am following. Make I know. Oya, muna do o. If you are following, just type I am following. Make I know say na human being I dey teach. Because some of you might have slept off and I'm teaching air. Type if you are following. Okay, Clara, at least one person, Imelda is still with me. Very good. Let's continue. Now, let's continue. So, as I was saying, this is not organic, but you need to understand this thing if you're going to understand bonding. You get. So, let's continue. Let's continue what I was describing. So, these things we talked about now are the different quantum numbers, and I've indicated what they are. So, take note of the fact that when we are considering sorry, where's my pen? My laptop is acting up. Sorry, don't mind me. So, true. Okay, so back to what I was saying. So, I was saying something. I said once you are considering carbon, we would not go further into discussing these things in details. All you need to know in carbon is S and P. And I said in S is 1 small block, P is 3 small blocks, D is 5, F is 7 small blocks. You get, and those are the degenerate orbitals. 3, 4, 5, basically 7 small blocks. Each of these small blocks can only contain a maximum of 2 electrons. So just have that in mind, that the highest that can enter here is 2 electrons of opposite spin. And this is what we refer to as Pauli's exclusion principle. Let's move ahead. Now, having mentioned this, what's the next thing we need to know? If you write a symbol of an electronic configuration, it would give us 3 pieces of information. The first one is this guy. This particular number here is what we refer to as the energy level. It indicates the energy level. Any number where they write here, like if I write 1s2, 2s2, 2p3, this for this first guy now, this orbital is in energy level 1, this s here is in energy level 2, this p here is in energy level 2. It's important to understand these things. Okay, moving ahead, this next one is what indicates the subshells. Subshells. Now, this subshell is indicated by the azimuthal quantum number. So just have this in mind, that this letter here is the subshell. Why this number that is hanging here is the number of electrons in the subshell. So just have that in mind, that these are the features of an electronic configuration. Now, why am I saying all these things? We are going to discuss bonding. And for us to discuss bonding, we need to first understand the different types of subshells. Now, the first subshell we are going to talk about is the S subshell. The S subshell, the first feature you need to know about the S subshell is that it is spherical in shape. Let me put out a diagram to show us this thing. Okay, S subshell is spherical. P subshell has what we call a dumbbell shape. Dumbbell na all this, if you sabi all these weights wey dey use one hand carry, well, make I another thing to know P subshell is figure 8. That's how the shape is. Let me put up a, let me try to increase this my screen so I go show una. And where is my video capture? Okay, let me increase this my camera so you guys can see what I'm showing you. Okay, now if you look at this structure now, I presume you can see it. I don't know if you can see, shall I don't go overdo. Sorry, I want to arrange my camera make una dey see am. Sorry. Now, if you look at this particular structure, this is the way an s orbital should look. It's spherical. That is to say, if you are representing an s orbital, you should represent it as a spherical shape. I'm still going to show you a pictorial diagram to talk about that. So once you consider s orbital, you are looking at something that is spherical. Because I think I've come across a question in one of your exam past questions where they asked you guys to identify the shape of the s orbital, spherical. Another reason you need to know it is because you could be asked to draw or show a diagram representing an end-to-end overlapping or side-to-side overlapping between S and P. If you want to represent the S, simply draw a circle, finish. The P orbital is dumbbell or figure 8. I said the P orbital is dumbbell or figure 8. When I say figure 8, it means that it has this shape. When you are considering the P orbital, it has this shape. Please, I presume you all can see what I'm doing. Make I know whether my camera dey properly positioned. Shey una dey see am? Mona talk o. Sorry, I misplaced my S subshell, so I was looking for it. Okay, so as I was saying, guys, that once you are considering S subshell is spherical, if you want to represent it diagrammatically, you have to show a spherical structure. Then, if you are considering your P, which are the two we are going to be considering majorly for today, you are looking at a dumbbell shape of simply figure 8 shape. Okay, now having said that, why do I need to talk about these representations? Listen, it's very important when we are going to start discussing overlapping and sigma bonds and pi bonds and how they are formed. But just note this: S is spherical, P is P is dumbbell. Okay, let me even give you the rest of them sef before I continue. D subshell is double dumbbell. Dumbbell na that thing wey dey carry as weight, but if you know dumbbell, just figure 8. Double dumbbell means figure 8 into 2. So if you have just one figure 8, this is P. But once you have figure 8 that is like twice of figure 8, is something like this. That is what we refer to as the D subshell, basically. Then F finally, F subshell has what we call a diffuse shape. When you say it is diffuse, it means it's constantly changing. There is no constant shape for F subshell. But in this particular organic chemistry, we are going to be considering two, S and P. Let's continue. Now, having said this, what's the next thing we need to take note of in this our small study that we are doing? Let's come back to electronic configuration. I had to just mention those things so that we will know. Now, carbon is represented like this, which means it has 6 protons, and because it's neutral, it also has 6 electrons. If we are going to fill or write the configuration, it's going to be 1s2, 2s2, and 2p2. If you notice, I kept filling until I got to 6. Once I got to 6 electrons, I stopped. And that is that. This is the electronic configuration of carbon. And if I'm to represent it by shell configuration, I'll have one block for S. Once it is S, it's just one small block. Here there is 2. But once it is P, you have 3 blocks. Now, 2p2 means that there are 2 electrons. According to Hund's rule, you have to give everybody 1 before you start pairing. So this is the normal configuration of carbon. Now let me tell you one special thing about carbon. This is important because so many questions have been derived based on this thing. So listen. The special thing about carbon is this, that it forms covalent bond. And when you talk about covalent bonds are formed when you share equally, which means if I bring 1, you will bring 1. In this case now, the only electrons carbon can bring is just 1 here and 1 here. If there is going to be sharing, it will bring 1 here, so that another element will now pair and bring another one that will join this. Another element will pair and bring another one that will join this. Because this place is empty, it cannot form a covalent bond with this empty space. So just have that in mind. Which means if carbon is to bond with its normal electronic configuration, it can only bond here and here. There is this special thing that now happens to carbon that is not always prevalent, or in most cases you might not see everywhere. The special thing is this: carbon will excite one of these electrons from here, and once it excites it, it will move it from here into this empty orbital. So if you write the configuration, you will now have 1s2, 2s. Remember, 1 left here and went here, which means it will now be 1 remaining here, and then we'll have 2p3. Now let's draw the orbital configuration. There's a simple reason I had to do this. Now if you draw the configuration, you have 1 electron here, and how many electrons here? You have 1, 2, 3. Total number of electrons is still 6. But with this particular configuration, you find out that carbon can share here, it can share here, here, and here. Remember, covalent bond is the bond that carbon can form. And covalent bond means if I bring 1, the other person that is combining will also bring 1. If I bring 2, the other person brings 2. So here, carbon can now bring 1, another element brings 1. Bring 1, bring 1, bring 1. So you have that because it is sharing equally. You are going to have 4 spaces for sharing instead of 2 as it should have been. So that is one thing carbon does to enable it to form multiple compounds. This is carbon in its ground state. And this is carbon in its excited state. So just in case you are asked to write the configuration of carbon in its ground state, this is what you are going to do. But when they say in its excited state, it moves one electron here. The major reason it is exciting an electron is so that it can now have 4 spaces for bonding. Now, what should you write about this thing in your jotter? Write: carbon atoms have the ability to form only 4 bonds. You can also write it as there are only 4 bonds that can be formed by carbon atoms. So put that down. Carbon can only form how many bonds? Can only form 4 bonds. And I told you what gave it that ability. It excited 1 electrons from here and put it here, such that you now have 1 1 1 and it can form 4 bonds here. Remember, the bonding is an equal sharing, and that's what we refer to as covalent bonding. So please put this down. Make sure you take note of this. Carbon can only form 4 bonds. Okay, let's move ahead. I have this question I think I got from one of your exams or your exam past questions. Let's look into this. Let me put it up on the screen. I presume if there's any question, you are permitted to ask once you have a question. Please ask questions if you have. If not, we'll just move ahead. Okay. What have you want to do now? Yes, question. Let me find. There's this question I came across. I think we should take note of that. Okay. Yeah. Okay. Very good. This is the question. So yes, can we try answering this question? Why do we think? Why can't an organic compound have the chemical formula C2H7? Why is it impossible for an organic compound to have the chemical formula C2H7? It's practically impossible. Who can tell me why? Okay, I think I'll have to answer this one. Am I getting any answer? Or should I just answer? Okay, before I continue or come back to this question, Praise was asking what is the excited state of an element. When you say an element is in its excited state, it means that the electron, one of the electrons in the energy level has moved from its normal position to somewhere else. Once there is a change from the normal energy level to a higher energy level, once an electron moves from a particular energy level to a higher energy level, it automatically changes that element into its excited state. That's basically what I mean when you say that it's in excited state. And I told you what happens in the case of carbon with respect to its excited state. Yes, I'm still with you guys. Is there any reason? Does anybody have an answer to this question? Okay, I'm going to answer. Let me just answer the question. Let me just answer the question for want of time. So, as I said, the question says, why can't an organic compound have the chemical formula C2H7? I'm going to answer it. Let me just go back to my board. Okay. Okay, so I'm taking this whole thing out. Now, the answer is simply based on the number of bonds carbon can form. Once you have C2, it means that 2 carbons are joined. Now, let's fill this particular carbon atom with hydrogen and see what happens. Remember, have in mind, carbon can only form 4 bonds. Oh yeah, we have gotten the 2 carbons here. Let's now fill hydrogen. If we put 1 hydrogen here, first of all, we said it can only form 4 bonds, which means it has formed 1 here on this guy now. This carbon has 1 here. So the remaining for this carbon is now 3. 1, 2, 3. Fill it with hydrogen. Remember, carbon can only form 4 bonds. In this carbon now, you have 1, 2, 3, 4 bonds formed. You go to this carbon, it has formed 1 here. So the remaining is 3. 1, 2, 3. So if we happen to write this formula now, you are going to have C2H6. So if you have to answer that question, why is it that you cannot have C2H7? There is no longer space. Reason, carbon can only form 4 bonds. And once a carbon atom bonds with 4 different atoms or has 4 bonds, automatically it becomes filled. It can't form any other or attach itself to any other thing. So if you want this thing now to form C2H7, you will need to attach another bond, which is impossible. Carbon can only form 4 bonds, and that is why you cannot have C2H7. If you have any confusion with respect to what I just explained, please indicate. Oh, sorry, this is supposed to be bad. This is correct. This is bad. Why? Carbon can only form 4 bonds, and if you put 2 carbon and fill it, You have one bond here already, so 1 2 3 4, e don full. Not no other hydrogen can enter here. You have carbon, one bond dey here, the remaining na 3. If you fill 3 hydrogen, no other one can enter. The total that can enter in 2 carbon atoms is 6. Are you getting what I'm saying? That is when you are dealing with single bonds. We'll still talk about the other types of bonds, but just have that in mind that carbon atom has the ability to form just 4 bonds. Is this clear? I would really appreciate it if, oh my god, I did not remove the question. Oh, let me remove it. I'm sorry about that. I did not see that initially. Let me remove the question. Sorry about that. Where is the question again? And I was just talking. Okay, let me re-explain. Okay, so now the formula is C2H7. They say, why can't you have C2H7? It's very simple. The first thing you need to understand is that carbon can only form 4 bonds. Can only form 4 bonds. So let's consider that. Now, if you check this thing, first of all, 2 carbon atoms is just this. One bond has already been formed here, which means that this carbon atom has formed 1. The remaining is 3 for this carbon. So hydrogen, hydrogen, hydrogen. This carbon don't full because it don't bond to 4 different things, or it don't form 4 bonds. Once it has 4 bonds, it is filled up. We go to this carbon, it has 1 here. The remaining it can form is now 3. And once you fill it up with hydrogen, this one don't full. Now, they say C2H7. What can be formed is C2H6 because carbon don't full. So you cannot have C2H7 because carbon atoms can only form 4 bonds, and there is no other place to attach it, basically. So if you are answering this question and they ask you, why is it that you cannot have a compound called C2H7? Simple, because carbon can only form 4 bonds. You can't have CH5 too for the same reason. One carbon atom can only be attached to 4 different bonds, and once you have that, that's your answer basically. Sorry, is there any confusion with respect to what I just said, so I can move ahead? Is there any confusion? I think I've removed the picture. It should have reflected by now. Okay, if there's any confusion, please indicate. Okay, I'll have to just move ahead. Monoserial, I think you have to like push forward to click on the live button. Click on the live button. Alright, let's continue. I presume this is understood, so I have to push ahead for want of time so that we would finish everything we are supposed to do in today's class. Now, this is that's that about electronic configuration. That excitement of one electron is what gives carbon the ability to now join on 4 sides. Remember, let's start with catenation. Catenation, it can join. Now imagine not just that it can join to form as many carbonate chains as possible. It can now join to form those chains on 4 different sides. We are looking at the special properties of carbon that enables it to serve or produce multiple organic compounds. Okay, so that's that. Now the third thing we are going to consider is bonding of organic compounds. It's a very broad subject matter, but I'm going to try to discuss the parts we need here. We would further discuss others in the next part. So you have bonding of organic compounds or in organic compounds. Now, I am going to, before I get into discussing the bonding in organic compounds, I'm going to give you a little description of chemical bonding generally. The first thing I would like to say is, when you say bonding, you are looking at joining of 2 things. You get 2 or more things. Once 2 or more things are joining, you are looking at a bond. You get. And chemical bonds are usually formed as a result of 2 major things. Number 1, electron transfer. And number 2, electron sharing. Any bond you see that is a chemical bond that exists, These are the two things that must happen for this particular bond to be formed. And what is the reason we need to do or perform chemical bonding? It's very simple. Stability is associated with a completely filled outermost shell. Let me put out a shell configuration for you to understand. Let's consider the shell configuration of carbon. You know, in the first circle, you have 1, 2 electrons. Then now the others will now be having 8, 8. We sabi this thing now, secondary school stuff. I presume you did it in first semester. Carbon has 6 electrons. This is indicating protons. So, but why I'm saying 6 electrons and 6 protons is because it's neutral. You get. But this is 1, 2, 3, 4, 5, 6. Now, if you look at this configuration, the outermost shell has 4 electrons, and these 4 electrons is not filled. Once you are considering stability, stability is associated with a completely filled outermost shell. Like if you consider something like neon, neon has 10 electrons. So let's draw it. 1, 2. Then we continue. 3, 4, 5, 6, 7, 8, 9, 10. Between these two different atoms now, you will find out that neon is more stable. Why is neon more stable? Neon is stable simply because it has a completely filled outermost shell. Carbon is not stable. Why is it not stable? Because the outermost shell is not completely filled. So have that in mind. The reason chemical bonds exist, or the reason it is important that you have formation of chemical bonds, is for one simple reason. What is that simple reason? The simple reason is to ensure that the I think, I'm not sure. Okay, sorry guys, there was a little glitch in. Like I said, don't come back. There was a little glitch, but it has been resolved. Sorry, I was just trying to. Okay, I presume we are still here. Let's just continue. Okay, so as I was saying, Adekomo, make the phone on finish. Sorry, if you guys would just excuse me for a little while, I need to resolve my internet connection issue. There's a little glitch, okay? Okay, I think we are still here. Sorry about that. There was a little internet issue. Can you please indicate if you are still around? If you can hear me clearly, indicate if you can still hear me? Oh, nice. Thank you. Okay, I just wanted one person to just indicate that. Let's continue. Um, yes. So what I was saying is the reason you have bonding, whether it's organic or inorganic, is to make sure that the outermost shell is completely filled. And carbon's outermost shell, if you notice, is not completely filled, but that of neon is completely filled. The two ways to bring about complete filling of outermost shell is number one, electron transfer, number two, electron sharing. Now, these two things is what now lead us to the different types of bonding we have in chemistry, which is important to take note of. So I'm going to just highlight them basically. I told you what I just wrote for you are the different ways or the different mechanisms required for chemical bonding. I said that the two ways to ensure that there is chemical bonding is either by electron transfer or by sharing of electron. Now let's consider the types of chemical bonds. Now, under chemical bonding, bonding generally is classified into two broad parts. The first part is what I refer to as intramolecular or interatomic. And the second part is what I refer to as intermolecular. Now let me briefly describe this thing. I have two molecules of water. Let me just draw the structure of water. So this is basically a Lewis structure of water. Now, when I'm considering this first part, the intramolecular or interatomic, intramolecular has to do with one molecule. When I'm checking the bonds between the atoms inside one molecule, that's intramolecular bonding or interatomic bonding. So if I come to water now and I'm checking between this hydrogen and oxygen inside this is one molecule. Have that in mind. This is one molecule. This is another molecule. So when I'm checking the bond between the atoms that are inside one molecule, what I am considering here is interatomic or intramolecular bonding. One of the ways you could remember this thing is for those of you that did, I think you guys are going to do 7 ZEP. I don't know, but in your secondary school jam period, you did intra-specific competition and inter-specific competition. Intra is between when you're talking about the same species, that's intra-specific. But inter is between different species. So that's the thing. In intramolecular is inside one molecule. Then in intermolecular is between different molecules, whether of the same substance or different substances. So when I'm considering the bond between this molecule of water and another molecule of water, I will say that this one is hydrogen bond. I will still discuss these things. I'll call this one hydrogen bond. But if I'm considering the bond between hydrogen and oxygen inside water, this is what we refer to as covalent bond. Alright, let's discuss these things in details. So as I said again, that intramolecular or interatomic is the one you find in between atoms inside a molecule, while intermolecular is between different molecules. So when you have a molecule and another molecule, that's intermolecular. But when you are considering the atoms inside a molecule, that's intramolecular or interatomic. There are 4 major interatomic bonds. And what are they? Ionic. Another name for ionic is electrovalent, covalent, dative, and finally metallic. So these are the 4 interatomic bonds that you can have. Then when you are considering intermolecular, you have van der Waal, you have dipole-dipole, and then finally you have hydrogen bond. Okay, so you can take a screenshot of this. We're not going to discuss these things in details, in this class. We're going to discuss it in details in another class. What I'm just going to highlight is the bonding with respect to carbon. That's what I'm going to talk about. Bonding with respect to carbon. So you can screenshot this thing. We're going to come back to discuss bonding generally, because we're going to be mentioning the dipole-dipole forces, which is actually what uh, defines solubility of organic compounds. Normally, organic compounds are not supposed to be soluble in water, but because of this dipole-dipole and hydrogen bond, you find out that some organic compounds are soluble. We'll discuss these things in a different study or in a different class, I meant to say. But for this class, we are only going to be considering two major types of bonds: ionic and covalent. Let me just give a highlight, like major things you need to take note of. Ionic bond is the type of bond that is formed between ions. In fact, one general thing that can help you identify ionic bonds is that ionic bonds occur between metals and non-metals. Once you see a metal and a non-metal joining together, just note that what is between them is an ionic bond. So if I have something like Grignard's reagent, that is made up of an alkyl group attached to uh, halogen and magnesium. This is what we refer to as Grignard's reagent. We'll still talk about it under your haloalkanes or halogen derived organic compounds. Now, did you notice that there is a metal here and a non-metal, and you have an organic carbon chain? Now, it implies that there has to be an ionic bond formed here. Once a metal is joined to a non-metal, just note that ionic bond is there. And in ionic bond, it involves complete transfer of electrons. Complete transfer of electrons. Covalent bond, on the other hand, is between non-metal and non-metal. So when a non-metal joins to another non-metal, the likely bond that is there is covalent. So if I have carbon and hydrogen joined, what is this bond? Covalent. You don't need to think about it. Once you see two non-metals joining, like in water, water is hydrogen attached to oxygen. What type of bond should be in water? Covalent. Why? Hydrogen is a non-metal, oxygen is a non-metal, so the type of bond that is formed there is covalent. Now, another thing that you need to take note of in covalent bonding is that it involves equal sharing. Let me explain what I mean. Let me use diagrams to describe this. So if I want to consider the covalent bond between let's consider the least or smallest organic compound, methane. Remember I told you that can form carbon can form 4 bonds. If we consider the structure of carbon, it is 1, 2, 3, 4, 5, 6. This is carbon. Now let me put hydrogen. Now if this is hydrogen, hydrogen only has 1 electron. If there is a covalent bond to be formed, carbon will contribute 1, hydrogen will contribute 1, and the two of them will share it. Which means carbon will donate only this 1, while hydrogen will bring its 1, and the two of them will be sharing this 2. It implies that there has to be another atom here. So another hydrogen will come and bring 1. This is hydrogen, hydrogen, hydrogen. And if it brings 1, carbon on the other hand will bring its 1. Sorry, this diagram has a little bit of, okay, so as I said, hydrogen brings 1 electron, carbon will bring 1. Another hydrogen comes here and brings 1 electron. So let me use a different color so it will be like very clear. If another hydrogen brings 1 electron, it implies that carbon has to only contribute 1. If another hydrogen here brings 1 electron, it implies that carbon only has to contribute 1. If another hydrogen brings 1 electron, carbon contributes 1. So why is this a covalent bond? This is hydrogen, mind you. This is hydrogen. This is hydrogen. This is okay. This is hydrogen. And this is carbon. So notice this. That carbon brought 1 electron, hydrogen brought 1. What type of bond is here? Covalent. Why is it covalent? Because they are sharing it. And not just that they are sharing it, they are sharing equal number. It's very important to understand this, because I'm going to talk about heterolytic fission and homolytic fission. But before you understand that, you need to understand first that in covalent bonding, covalent bonding, sharing of equal number of electrons. That's the first thing you need to take note of. In covalent bonding, you have sharing of equal number of electrons, which means if carbon brings one, the other element will bring one. Okay, let me consider another element. For instance, let's consider another compound. I've told you what you used to know covalent bond sharp sharp. Once you see say two non-metals are joined together, those two non-metals are joined by a covalent bond, most likely. You get. If you see a metal and a non-metal, it's ionic. You don't need to think about it twice. Another thing to know ionic bonding is anytime it involves a complete transfer and that you have formation of ions, just know it's ionic. And now let's continue. Now, imagine for instance you have something like let's say you have your methanonitrile. Methanonitrile. Now the methanonitrile it implies that you have just one carbon atom which forms a triple bond with nitrogen. You get. So let's draw the structure. If we're looking at an orbital structure, if this is carbon is 1 2. So I'm going to draw it in such a way that it brings 1 2 3 4. Then nitrogen on the other hand has 7. 1 2 6 7. Okay, so this is nitrogen and this is carbon. Now it is important to note that if you are going to have a completely filled outermost shell, the two of them have to share equally, and in this case nitrogen brings 3. How many did carbon bring? Carbon brought 3, and this is what actually led to the bond called the covalent bond. Why? Carbon is non-metal, nitrogen is non-metal, and they are sharing. Not just that they are sharing equal number. Now what this thing automatically means is that if for instance now I want to count the number of electrons in the outermost shell of carbon, if you want to count it, sorry, let me take this out. So you find out that this particular arrangement, carbon brought 3, nitrogen brought 3, and this is what? Covalent. This is covalent. Why is it covalent? Because you are dealing with an equal sharing. Okay, now watch on this other side now. Hydrogen will now be attached because the formula of methanonitrile is C triple bond to N, and then you have one hydrogen. This is basically the structure. So which means we need to draw one hydrogen here. So this is hydrogen. Now, if we are to count the total number of electrons in the outermost shell of carbon, it is going to be 1 2 3 4 5 6 7 8. You go count those ones where they count. All of them, they don't join them together. So you count all of them together. This is 1 2 3 4 5 6 7 8 for carbon. If you go to hydrogen, the outermost in hydrogen will now be 1 2. If you go to nitrogen, outermost in nitrogen will now be 1 2 3 4 5 6 7 8. So you have that basically as the structure of your methanonitrile. So why is this referred to as a covalent bond? Because number one, it is between non-metals, and then it involves sharing, equal sharing. It involves equal sharing. Okay, having said all this, please, I would like to get your responses. Is there any confusion so far? Is there any confusion so far? Can we please indicate if we are confused so that I can re-explain? If not, I just want to move ahead. We have to finish this particular thing today. Yes, is there any confusion so far? Please indicate. I would like to get your responses before I continue. Uh-huh. Is there anything I need to explain? If not, just say move ahead or go on. You get. Make I know whether or not human being I see the teach. Abi una don go sleep. Mona talk o. Mona talk. I dey wait now. Okay, Ozemena Priest says it's good. Okay, nice. Okay, okay. I'm coming. Confirm say all of us still there together. Okay, okay, okay. I should explain this again. Clara, Imelda. Okay, okay, okay. Now, Imelda. Okay, I will explain, but let me just confirm one or two things. Very good. Now, in covalent, if you bring one as an atom, first of all, is in, once you see two non-metals, once you see two non-metals, begin to suspect covalent. Now, how will you be sure that it's covalent that is between them? If a particular atom brings one and the combining atom also brings one, it means that they brought equal number. Like check for instance, this is carbon, this is nitrogen. Carbon brought three, nitrogen brought three. It means that between this carbon and nitrogen, there is a covalent bond. How many covalent bonds? Three covalent bonds. One, two, three. Why is it a covalent bond? The two of them are sharing it. You get. I have just given you one way to notice that once you see that two non-metals are together, start suspecting covalent. How will you confirm? If they contributed equally to that particular bond, automatically it is covalent, basically. So that's the first understanding I want you to have of this. If there are further confusions, just don't let it confuse you now. We'll get to describe, add more things to this thing, but this is the first and basic thing I want you to understand. Now, amongst the four interatomic bonds, the strongest is covalent bond. Yes, the strongest is covalent bond. Why am I saying this? This particular strength of the covalent bond is what is responsible, and it is the exact reason for which you would have that organic compound reactions are slow. So if you have a question and they say, why is reactions of organic compounds slow? The simple answer is because organic compounds usually possess covalent bonds which are strong. You get, so it's harder to break covalent bonds than ionic bonds in chemical reactions. Ionic bonds are basically ions. There's no like direct joining necessarily. You get, in covalent bond, the two of them are have completely filled as a result of their joint effort. So everybody is putting together something and holding it together. That is in covalent. But in ionic bond, they the transfer just occurs and one of them becomes positive, the other one becomes negative. That is what leads to the attraction. So just have that in mind, that covalent bond is a very strong bond, and because it is very strong, that is why chemical reactions does not readily occur in organic compounds. Okay, so you have that. So if you see a question and they say what is the reason for which um organic reactions are slower than ionic reaction. Organic reactions are slower because in the organic compounds, what you have there is covalent bond, which is a relatively very strong bond, possibly strong. It's stronger than, we can say it's stronger than the ionic bond. So that's that basically. Okay. Having said this, I think I'll have to move ahead. Now, the next thing we will need to understand is that, as I said, the two major bonds you are going to find in for now that we are going to discuss, the two major interatomic bonds that you will find majorly in organic compounds are your ionic and your covalent. This one is usually between carbon and metallic ion. Carbon and metallic ion, or any other cation. While covalent is between carbon and any non-metal. Remember here, transfer of electron, here equal sharing. We are still going to discuss bonding later. You get, I'm going to take my time to describe all these things, but I'm not going to discuss it now. We'll have to go a little bit further into the study before I start talking about it. And we'll now discuss the inductive effect, the steric effect, and how it affects stabilization. These are things we are going to be discussing after we are done with this basic understanding. Okay, now, having said this, before I move further into other things, I would like to describe the two types of, or the two ways of forming covalent bonds. So have that in mind. That covalent bonds, there are two major processes or methods of forming covalent bonds. You can say covalent bonds, covalent bonds. Whether you say they are classified into two, there are two major ways of forming covalent bonds. The first one is what we call end-to-end overlapping. The first one is what we call end-to-end overlapping, and the second one is what we call parallel overlapping. These are the two forms of covalent bonds, or the two methods of forming covalent bonds, generally speaking: end-to-end overlapping and parallel overlapping. Now, please remember that I said that the two major subshells we are going to be considering inside carbon or organic compound is S and P subshell. And I told you S subshell is spherical, P subshell is figure 8 or dumbbell. It's important you note this thing. Now, what is the end-to-end overlapping? Let me put up so that we can see the definitions as we are studying. End-to-end overlapping. Okay. So whenever I say end-to-end overlapping, I presume you can now see it. First of all, is that end-to-end overlapping, just as the name is basically, okay, as this what is written on the screen. This type of bond is formed by overlapping S to S, P to P, S to P orbitals at the heads or ends of their orbitals. Okay, that's that. Now I will come back to this, but let me explain or show you what I mean by that. Any form of overlapping that you are doing, when I say overlapping, see what I mean. Let me go back to my board. Please, it's important you listen here because these points might be very confusing. So let's do end to end. End to end. Now, if you have, for instance, a spherical orbital, you want to do end to end, and this is an s orbital. We are not considering the number of electrons, they just concentrate on the orbital. P orbital is going to be figure 8. If you are going to perform end to end, it means that you are going to join it, this head to this head. This is what we call end to end overlapping. End to end overlapping is basically the overlapping which occurs when there is a head to head joining of different orbitals. Once you have head to head joining or head to head overlapping, that is what we refer to as end to end overlapping. I'm going to like increase my my uh my camera so that you guys might see what I'm trying to do. Okay, now if you noticed, initially we talked about these two guys, your spherical orbital, which is S, and your double or figure 8 orbital, which is P. Now if you are going to do end to end overlapping, it means that the head of the P orbital will join with the head of S orbital. If I overlap them, let me try to overlap them so that we'll see. Once I have this, if you notice, the head of the P is joined to the head of the S. This is what we refer to as end-to-end overlapping. It's very basic. Once the head joins to the head, if it overlaps like this is what we refer to as end-to-end overlapping. Basically, I hope this is understood. Please, if you do not understand, indicate. If you do not understand it, indicate. I still there the way to na indication. No. Okay, Samuel Oscar. Covalent is between non-metals. Yes, may we talk oh. Abi everybody don go sleep. May we talk. That's what we refer to as end to end. Once the head joins to the head, that is the form of of covalent bonding that we refer to as end to end. Mona talk oh. Okay, so let's put up the definition basically. So, having described it, I believe it's easy to understand. So, end-to-end overlapping is the type of overlapping that is formed by, okay, I forgot to say something. When you are considering end-to-end overlapping, the type of bond end-to-end will give you is what we call a sigma bond. So that sigma bond is what is formed by doing end-to-end overlapping, which involves overlapping the heads of S to S, P to P, S to P orbitals at the heads. Once you are overlapping at the heads, what you are doing is end to end. If you notice, if I'm to draw the overlapping now, I'm going to join them. This is now, okay, let me go back to my board. If I'm going to draw it as overlapping, I will have that this s orbital overlaps p orbital. Remember, this is figure 8. And I'll put one electron here. A bond will now be formed between these things. This is what we refer to as end-to-end overlapping. So it occurs between S and P. It occurs between P and P, or S and S. So take note of this, that once you are dealing with end-to-end overlapping, you are considering an overlapping where it occurs at the head of the orbitals. Once it occurs at the head of the orbitals, that is what we refer to as end-to-end overlapping. Please, if you have questions, indicate so I can continue, because this is one important part. Okay. Yes, what do we think? Nobody is talking again now. Una don go sleep, make una talk oh. Okay, so I think I'll just have to continue, sha, basically. Okay, so that's basically what you talk about. When it is end to end, the implication of the statement is that the heads of the orbitals would be overlapping. If you can see what I'm illustrating, the head of this s orbital, which is the spherical one, overlapped the head of the p orbital, which is the double dumbbell one. So once you have this kind of arrangement, this is what we refer to as end-to-end overlapping. Now, one major thing about end-to-end overlapping, number one, or things to note, you can write that down. Things to note about end-to-end overlapping is that it leads to the formation of sigma bonds. Things to note about end-to-end overlapping, it leads to the formation of sigma bonds. End-to-end overlapping leads